Hello everyone. In this talk, I'll be presenting Spider. It's a technique for enabling fast patch propagation in related software repositories. I'm Arvind Mechuri. This is joint work with various researchers from SecLab at University of California, Santa Barbara. Before understanding Spider, let's look at security patch propagation. So in case of open source software repositories, when a security patch happens to the main repository, a CVE number is usually announced, and the vendors are expected to port the security patch from the main repository to the corresponding repositories. Unfortunately, in case of smartphone ecosystem, there is a huge delay in propagation of the security patches from the main repository to the vendor repository, even in the presence of CVE numbers. Furthermore, there have been security patches which do not have a CVE number, so which puts vendors in blind because vendors have no idea to know the severity of the patch without knowing a CVE number. However, since it is open source, an attacker can look at all the patches that go into the open source repositories. Now, attacker can figure out from the security patch the underlying security vulnerability. With this information, attacker can exploit all the vendor software that has the underlying vulnerability because vendors did not port the corresponding security patch. And this problem happens in real too. For instance, there was a security vulnerability in Android identified in last year. However, the patch for this was already made to the mainline Linux in December 2017. Unfortunately, the patch did not have a CVE number. Furthermore, there was a security issue with VLC player because it was using an old version of libbvml. Since libbvml fixed the vulnerability but did not assign a CVE, this caused a huge security issue on Ubuntu 18.04 systems. How can we solve the propagation of patches? One of the main important things that we need to solve in automatic patch propagation is testing, because any patch, when automatically propagated to the vendor repositories, has to be tested across various software configurations of the underlying software. And testing of various configurations of low-level software, such as kernels and bootloaders, is challenging without hardware. And most often, the testing requires manual intervention. Our intuition is that most of the security patches are fine and they do not need testing. So based on this intuition, we set ourselves the goal. Can we statically verify that the given patch does not adversely affect the functionality of the program? And we also want our technique to satisfy two requirements. The first requirement is that it should only rely on original file and the patched file without any additional information such as commit messages or build information or any other information from the source repository. Furthermore, we want our technique to be fast, lightweight, and scalable. The reasons for this requirements are ease of adoption and deployability. We want our technique to be easy to be adoptable and deployable by the vendors without much changes to their build environment. Spider is such a technique that satisfies both the requirements and it identifies safe patches. Specifically, Spider is a verification technique that automatically identifies patches that do not adversely affect the functionality of the program. And we call such patches as safe patches. To do this, we first need to define what we mean by functionality of the program. We can define functionality of a program in terms of its inputs and outputs. Specifically, we consider a patch not affecting the functionality if, for all expected inputs, the output of the patched program should be same as that of the original program. If that's the case, then we can consider the patch to be safe. However, this is not always true, because we can have patches that instead of changing the output, they make new inputs. Specifically, the patch which is shown on the slide, it includes new input as a new expected input of the program. And this new input might break the program. So this condition is not sufficient. We need to add additional constraints. We can add additional constraint saying that the patch, in addition to having output equivalence, the patch should not allow any new inputs into the program. If you look at the patch as shown on the slide, so here this patch actually, instead of increasing, it decreases the inputs that go into the program. If you consider A as input to the program, this patch is actually restricting the input space to be less than max length. This patch is actually fine because instead of increasing, it is decreasing the input space. Based on these two observations, we define what we call safe patch conditions. Specifically, we consider a patch to be safe if it satisfies two conditions. The first condition is non-increasing input space. Here, the patch should not increase the valid input space of the program. The second condition is output equivalence, where for all the valid inputs, the output of the patched program should be same as that of the original program. To verify these two conditions, we can define these two conditions at function level. And if these two conditions hold for each function, then we can say that these two conditions hold for the entire program. Now let's define our condition C1 at function level. So at function level, we can define condition C1 as follows. The patch should not increase the valid input space of the function. In other words, all valid inputs to the patched function should also be valid inputs to the original function. This can be represented by the first order logical constraint as shown on the bottom of the slide. Here, for all inputs I, if I is a valid input to the function fp, which is the patched function, then I should also be valid input to the original function fo. Now we need to find valid inputs to a function. How can we find valid inputs to a function? We know that input space contains valid inputs and invalid inputs. And invalid inputs are the inputs that are considered as invalid by the function. Specifically, these are the inputs that the function doesn't know how to handle. These are the inputs that are rejected by the function. This means these are the inputs that reach invalid exit points. Let's look at an example. This is a simple function foo. We can see that it has two exit points, return 0 and return -1. And intuitively, we can see that return -1 is an invalid exit point. So all the inputs that can reach return -1 can be considered as invalid inputs. Similarly, all the inputs that reach valid exit points can be considered as valid inputs. In our example, return 0, which is a valid exit point, all the inputs that reach return 0 can be considered as valid inputs. Now, how can we find valid inputs? Now, given a valid exit point, we can use control dependencies to identify the path constraints that control the reachability of that statement. Specifically, in this case, in order to reach return 0, any input should make the condition inside if false. This can be represented by the path constraint as shown on the right-hand side of the slide. So here, any input to reach return 0, it needs to make the condition inside the if false. Now, for the function that has multiple valid exit points, what we can do is we can do a disjunction of the path constraint of all the exit points. This gives us all the valid inputs to a function. Once we identify valid inputs to the patched function and the original function, then we can show that all the valid inputs to the patched function, the path constraint that represents valid input to the patched function implies the path constraint which represents valid inputs to the original function. Now to verify output equivalence C2, we can define the C2 at function level as follows. For all valid inputs, the output of the patched function must be same as that of the original function. So here we can see that for any input I, the output of the function fp when run with input I should be same as output of the original function when run with the same input I. To do this, we first need to define what we mean by output of a function. So we define output of a function as all the effects of a function that are externally visible, specifically its return value and all the writes made by the function to non-local data such as heaps and globals, and also all the function calls made by the function itself. Furthermore, we also consider all the changes made to the error handling basic block as something that doesn't affect the output of a function. The reason for this is the code in the error handling basic blocks is the code that tries to recover from an error condition and thus doesn't affect the output of a function. And output of a function, output actually depends on the data flow paths. Here in the simple function bar, here we know that the output of function bar is return statement 8. So this output depends on the data paths. There are two data paths in this function. The first path is D1, which happens when a less than 10 is false. And the second data path is D2, which happens when a less than 10 is true. So depending on the data paths, the output changes. And in order to verify output equivalence, in addition to capturing output, we also should capture the data paths along with along which particular output is produced. So once we capture data path and corresponding output pairs, we can use the first order logical constraint as shown on the slide to verify that when the output is same, the corresponding data flow paths imply. That means any input that produces output OI in the patched function also produces same output in the original function. However, enumerating all the data flow paths becomes tricky in presence of loops because loops induce potentially infinite data flow paths. To handle it, we use unrolling. Specifically, we unroll loops once. Furthermore, this gives us a challenge for patches that directly affects the statements which are within a loop. So to handle this, we consider all the patches that directly affects a statement inside the loop to be unsafe. Basically, we do not handle those patches. With these techniques, we did spider implementation. So here our implementation takes original file and the patched file. We first perform preprocessing, and then we parse the preprocessed output, which gives us control flow and data and program dependence graph. We then perform fine-grained diff technique, which is Gumtree. Here, Gumtree gives us all the statements that are affected by the patch at AST level. Once we know the statements affected by the patch directly, then we use dependencies in the program dependence graph to identify all the other statements that are data dependent on the statements that are directly affected by the patch. Once we know all the statements, then we use symbolic compilation to verify conditions C1 and C2. If C1 and C2 holds, we say the patch to be safe. Let's look at a patch. And here, the patch is shown on the slide. Here, the lines on the red are the lines that are removed by the patch, and the lines in green are the lines that are added by the patch. Now, to verify condition C1, we first need to identify all the valid inputs to the old function. The old function is shown on the left-hand side of the slide. Here, we can see the function has multiple exit points. However, it has only one valid exit point. Now, all the inputs that can reach valid exit point can be captured by the path constraint as shown on the right-hand side of the slide. Similarly, for the new function, it has one valid exit point, and corresponding path constraint is shown on the right-hand side of the slide. Once we capture the path constraint, we use symbolic compilation to convert the path constraint to corresponding symbolic expression. Basically, here we interpret each instruction using symbolic values for the variables. And for function calls, we use technique similar to theory of uninterrupted functions, where we use symbolic value, which represents function call with certain set of arguments. So using symbolic compilation techniques, we convert the path constraint to a corresponding symbolic expression as shown on the bottom of the slide. Similarly, for the new function, we do the same thing. However, here for the statements that are affected by the patch, we use new symbols. So for instance, here S6 and S7, these are present only in the path constraint of the patched function. So these are the new symbols added during symbolic compilation of the path constraint in the new function. Once we get the symbolic expression, we need to show that all the valid inputs to the patched function are also valid inputs to the original function, which is to prove the implication. This can be represented by the corresponding symbolic expressions, which can be reduced to mod exponents, as shown on the bottom of the slide, which obviously holds. That's why the patch satisfies condition C1. Now, to verify condition C2, we need to identify statements that affect the output and that are modified by the patch. So here, the statement that affects the output is k-free. However, this is in the error handling block. Based on what I mentioned before, the changes in the error handling block do not affect the output. Therefore, this patch does not affect the output and thus satisfies condition C2. Therefore, this patch is safe patch. Since Spider works only with the original file and the patched file, it has to make several assumptions. The first assumption is that the output of a function depends only on its arguments. The second assumption is that we do not consider dependencies through aliases. The reason for this is that to perform alias analysis, we need access to the entire program code base. Since we do not have it, we cannot perform alias analysis. And we use heuristics to identify valid exit points. And most of these heuristics are specific to system code bases, but these heuristics may not hold true for other code bases. So we need to be careful in order to apply Spider to other code bases that do not follow system code practices. Furthermore, we also assume non-adversarial patches. That means we assume the developer who made the patch to be trusted. We performed large-scale evaluation of Spider, specifically on 32 large open source code repositories, which included kernels, libraries, and operating systems. We also evaluated on 809 CVE fixing patches. In total, we evaluated on 341,000 patches. We identified that 19% of this 341,000 patches to be safe, out of which 58% of the patches are missing in at least one active fork. And on CVE patches, we identified that 55% of the patches are safe. That means even in the absence of CVE numbers, Spider could have helped in propagating all the 58%, 55% of the patches to all the vendor repositories. And we also ran Spider in security patch mode, where the patch, along with being safe, should also satisfy certain patterns common to security patches. Upon manual inspection, we identified that close to 2,000 of these patches are actually security patches, and they do not have a CVE number. Furthermore, close to 1,000 of these patches are missing in at least one active fork. This means there are close to 1,000 security vulnerabilities ready to be exploited in various vendor repositories. And this is an example of a patch that is made to the Linux kernel, which is a security patch and do not have a CVE number. With this, I would like to end the talk. Thank you.